Good morning, everyone. So next topic is dynamic programming. So far we have discussed about greedy method. Greedy method, it was talking about optimization. That is maximization of profit, minimization of loss. Whatever it is, we were looking for optimized result. In the same way, dynamic programming is also, here also we'll talk about optimization itself, optimization of the results, whether it's maximization or minimization, whatever it is, we will try to find out the optimized result So here also dynamic programming follows same intention is kept here in the dynamic programming. You'll see what algorithms will come, how it is different from greedy method. See, that question might be asked in exam, how exactly dynamic is different from greedy method. Okay, you'll see with example, knapsack, we have used greedy method in for knapsack in previous sections. Here we'll see knapsack using dynamic programming. Okay, similarly you can compare. So dynamic programming is again a optimization plan technique. If you have recursion, we'll try to remove that recursion and we'll try to solve it iteratively. Wherever we see recursive solution that has repeated calls for same input, we can optimize it using dynamic programming. And the idea is to simply store the results of sub-problems so that we do not have to recompute them when needed later. See, that is what happens in case of recursive functions. Okay, I will show with an example what exactly we are talking about. In dynamic programming, we'll divide the program into sub-problems and we'll solve them independently and store the result. And we'll make use of those results to solve the further problems which we have divided. Okay, that is the whole idea in dynamic programming. We'll divide the problem and we'll solve and keep those results and we'll reuse them to solve the further problem of that nature. Okay, if you do like that, this optimization reduces time complexity from exponential to polynomial. So if you apply dynamic approach, time complexity, there will be a huge improvement in time complexity. So that's all about dynamic programming. We shall see with an example. First, we shall see Fibonacci function. Okay, you know that this is the Fibonacci series. If n is less than or equal to 1, we'll return that value itself. If it is 1, we'll return 1. If it is 0, we'll return 0. Otherwise, return fib of n minus 1 plus fib of n minus 2. Okay, recursive Fibonacci function. Okay, this is a recursive Fibonacci function. Here, time complexity, it is exponential. Same Fibonacci function, we can do it iteratively. Here you can see, we know that if n is 0, fib of 0 is 0. If n is 1, fib of 1 is 1. So this we have removed here. Okay. Same Fibonacci series, we are trying to write it iteratively. And then from second, we will start I value is equal to 2 to n. I is equal to 2, I less than or equal to n, I plus plus. F of I is equal to f of I minus plus f of I minus 2, I minus 1 plus I minus 2. Return f of n. Okay, Fibonacci series recursive and this is iterative. So here time complexity, it will result in exponential. If you check the time complexity here, it will become linear. Okay, here there is no recursive call involved here. How it will improve, I will just show with an example. Fib of 7. Okay, I need to find out fib of 7. So first it will call fib of 6 plus fib of 5. Okay, Fibonacci recursive function I'm talking about here. Fib of 7 means fib of 6, Fibonacci of 5 it will call. Okay, it will go on calling. Recursive tree I have written. So fib of 6 if you call, it will call fib of 5, fib of 4. Again fib of 5 if you call, it will in turn call fib of 4 plus fib of 3. Fib of 4 it will call 3 plus 2. And again 3 will call 2 and 1. Fib of 2 means fib of 1 and fib of 0. Fib of 1 means it will return 0 and then it will return 1. 1 plus 0. So you will get the result for this. And again fib of 1 is, again it will call fib of 1. You will get 1. Fib of, see, just to find out Fibonacci of 7, can you see how many calls it is making? See, it is calling Fibonacci function so many times. Okay, if you keep counting, it is like just for number 7, it is calling Fibonacci function so many times. Are you understanding the complexity of recursive functions? Okay, it will call the Fibonacci function so many times. Instead of that, now if you use the iterative method, so Fibonacci of 7 is what? Fibonacci of 6 plus Fibonacci of 5. All right. Fibonacci of 6 is 5 plus 4. Fibonacci of 5 is 4 plus 3. 4 is 3 plus 2. Fibonacci of 3 is 2 plus 1. Fibonacci of 2 is nothing but 1 plus 0. So what we'll do, Fibonacci of 0, we know that it is 0. We'll store it. Fibonacci of 1 also, you know the answer, that is 1. We'll store it. Okay, iterative method. So what is Fibonacci of 2? Fibonacci of 2 is nothing but 0 plus 1. That also we'll store it in an array. Next, to find out Fibonacci of 3, I need Fibonacci of 1, which is there already in the array. And also we need Fibonacci of 2, which is also there in the array. Is it clear? So you will get Fibonacci of 3. Similarly, you will get for Fibonacci of 4, you need value of Fibonacci of 3 and 2. See, no need to call the functions, these functions again. If you store it in an array, whenever we need it, we will just simply take it out of array and we'll do the computation. Okay, Fibonacci of 5. Here on the right hand side, F4, F3, all these things you need not have to call because all those values are already present in the array. Is it clear? So if you can see here, the highlighted thing is we are calling the Fibonacci function this many times. But this light shaded thing, it was called in the previous. See here, so many times we have called Fibonacci. Here only these many times we have to call it. It will be executed and we'll store the intermediate results. And wherever we need it for computation, we'll fetch it from the array itself. You need not, we have saved these many number of calls. You can see here, light color things, these many number of calls we have saved. If you use the iterative approach, we have saved the computation by calling, making call for these many number of times, because those are the results which we have already computed. And if it is there in the array, just we can, if it is in one location, you just, whenever we need that for F4, it will be there in the array. Go and fetch it. No need to make the call again and again, because if I call for F4, it will call F3, F2, F2, F1. It will go on calling the Fibonacci again and again. So we are saving that time. Okay, so this is dynamic approach. Intermediate results, we'll save it in some places. And for further problems, we'll just use those intermediate results. Okay, sub problems, whatever we have divided, that results will be stored in a location. And in future computation, if we need it, we'll just fetch it from that array. We'll not call those, make them work again. Okay, that is this is one example for recursive Fibonacci and iterative, how it will differ. Okay, we again one topic is there. My task is to find shortest path in a multi-stage graph. Multi-stage means this is stage 1, stage 2, stage 3, stage 4. So in a multi-stage graph, if I ask you to find the shortest path using greedy method, if you apply greedy method, if you want to move from S to A, obviously greedy method will fetch the shortest distance from S to A. And A to B shortest distance is 2. And B to T shortest distance is 5. So greedy method will fetch this distance 1 plus 2 plus 5. Say I need to travel from S to T. And these are not undirected graph. Here, from here on, we'll be using directed graph. If this is the situation, if you are using for multi-stage graph, if you apply greedy method, this is how we'll get the solution. Okay, this graph is simple. When the graph gets complicated like this, okay, a little bit more complicated multi-stage graph, And you need to find out the shortest distance between S and T. Shortest distance means its cost should be less. And if you apply greedy method, what will happen? Greedy method, what it will do? From S, it will find out the shortest path. From S to A, it will go. Okay, 1. And then from A, see greedy method. We are in A. A from A, which has got the least cost rates, 4. A to D. It will go to D. And from D, there is only one path to T. Cost is 18. So greedy method, what it will do is it will take total cost will be 23. Okay, but that is not the best path from S to T. So shortest path will be cost of 9. That is S to C, C to F, and F to T. Okay, so there is one shortest path which which will lead to cost 9. So greedy method will not work in all the situations. Okay, for undirected graph, it was okay. It used to find the shortest distance. Now that is not the case. Okay, for this multi-stage graph, we have to find a way to find the shortest distance from S to T. Okay, in the exam, there will be a short question about multi-stage graph. Find the shortest distance in a multi-stage. Either they will give you the graph and ask you to find the shortest graph or distance, or they'll just give the question, find the shortest path. How you will find the shortest path in multi-stage graph using forward reference? Two types are there. Okay, forward approach and backward approach. Either methods they will ask. Explain how to find shortest path in a multi-stage graph using forward approach or backward approach. Okay, that question you will get for sure in exam. It's simple. One graph you have to draw, and those methods are also easy. Forward approach and backward approach. So first, let's see forward approach solution for shortest path in a multi-stage graph. Forward approach. See, my task is to find the shortest distance between S to T. Okay, S to T. And S to T means from S, we can go to the nodes A, B, C. Okay, distance of S to T. This is what I need to calculate, distance of S to T. To do that, from S, I can reach only A, B, C. Okay, so we have to select minimum among these three. Minimum of 1 plus D of A to T means distance of C. S is reachable only up to ABC. So if I go to T via A, what is the distance? Distance of A to T. Again, I have to calculate this one. Okay, minimum of any of these three things. 1 plus D of A to T, or 2 plus D of B to T. D of B to T means I will go to B. From B to T, what is the distance that you have to calculate? Or 5 plus C, that is from C, D of C to T. Okay, 5 plus distance of C to T. We have to calculate these three things. Distance of A to T, distance of B to T, and distance of C to T. If you get these three values, we'll add it to these values, 1, 2, 5. Whichever is minimum, that is the distance between shortest distance from S to T. So we have to calculate these three things. Okay, distance of A to T, distance of B to T, and distance of C to T. Okay, these three things we need to calculate. First, let's consider A. Okay, distance of A to T. We have just written the same graph here. From A to reach T, you can go through D and E. Okay, I need to go to T from A. You can go in this path, either from D or from E. So distance of A to T is equal to minimum of 4 plus distance of D to T. Okay, minimum 4 plus distance of D to T. Okay, there may be one more node here present here, but in our case there is no node. There is a direct path, so you can write down this distance directly. From A to E, E to T. Okay, so distance of 11 plus distance of E to T. So distance of D to T, we know that that is 18. Distance of E to T is nothing but 30. So this is 22, this is 24. Minimum among these two things is 22. So 22. Finally, we got the distance from A to T. Okay, minimum distance. There was two paths here. Among these two paths, 22 is the least cost. So which we have, which we will store. And then next is distance of B to T. Okay, distance of B to T I have to find out. There are three paths here. You can go to D and then T, or through E or through F. There are three paths here to find out the distance of B to T, which is nothing but minimum of D to 9 plus distance of D to T, 5 plus distance of D to ET, 16 plus distance of FT. Okay, so 9 plus distance of DT is 18, 5 plus distance of DET is 13, 16 plus distance of FT, which is nothing but 2. So among all these things, this is also 18 and this is also 18. Minimum distance is 18. Okay, distance of B to T. Okay, that distance is 18. Next, distance of C to T. Here only we can see from C to T there is only one path, C to F and F to T. That is 2 plus 2. That distance is 4. Okay, distance of C to T. I am trying to find out the distance of C to T. So we will save these things. We will calculate and we will save these things. See, you have to calculate this and you have to store it. Everything we'll calculate and we'll go on storing it in an array. Now, finally, we have to calculate the distance of S to T. Okay, this is the final thing which you need to calculate. S to T, which is nothing but 1 plus A to T, that is 1 plus 22. 2 plus B to T, that is 2 plus 18. And 5 plus C to T, that is 5 plus 4. Among these three things, this is the minimum. Okay, so that is the minimum distance from S to T, minimum cost distance from S to T, that is from S to C to F to T. So that is the minimum cost distance from S to T. Forward approach means first we'll calculate the distance of these three things, and then from this, what is the cost from A to T, cost from B to T, cost from C to T, that we will calculate, and then we will also calculate cost from D to T, E to T, and F to T. So finally, we'll find out, we'll add everything up, and whichever is minimum cost, that is the cost shortest path from S to T. Okay, this approach we call it as forward approach. Okay, forward approach to solve multi-stage graph problem. Okay, so this is the forward approach, dynamic approach, forward approach for to solve multi-stage graph problem. To find out the shortest path in case of multi-stage graph. Okay, first distance of these three things you will calculate, and distance of these things, and then finally we'll go on adding the distance. Whichever is the shortest distance, that is the shortest path. Okay, that is forward approach. Next, we shall see backward approach. See, only slight change in the approach. So we know the distance from S to ABC. Okay, that will write 1 to 5. Distance from S to ABC. Next, see, in the previous approach, what we were doing is we were trying to find out distance of A to D, A to T, B to T, and C to T, and from D to T, E to T. Here, what we are going to do is we'll try to find out the distance from S to A, B, C, and S to D, E, F, and then with the help of that S to T. So next, what I will try to find out is distance of S to D. What is the distance? What is the minimum distance from which I can reach D? Okay, there we were talking about distance of these nodes to the T. But here we are talking about distance of these nodes to S, that we will calculate, and we'll use minimum distance among these things, and we'll use it to reach T. Okay. So minimum distance. Now I will be trying to find out what is the minimum distance to reach from S to D. Okay, what are the path? Either I can go from A or from B. Okay, minimum of distance of S comma A plus distance of A comma T, comma minimum of distance of S to B and B to D. So this is 1 plus 4 and this is 2 plus 9. 2 plus 9. So what is the minimum distance? 1 plus 4. So this is the minimum distance to reach D. Next, I will find out minimum distance to reach E. Okay. See, first we try to find out the minimum distance from S to these things. Next, we'll try to find out the minimum distance from S to these things. S to E. Okay, distance of E to reach E, you can go from SAE, SBE. Okay, from C we cannot go to E. Only two paths are there. Okay, 1 plus 11, first path. Okay, 1 plus 11. Second one, 2 plus 5. Okay, 2 plus 5, which is nothing but 7. Next, distance of S to F. Okay, distance of S to F. I can go through B to F, that is 2 plus 16, or we can go through C, 5 plus 2. Okay, 2 plus 16 or 5 plus 2. See, now we have reached from S, we have reached D, E, F through minimum distance. Okay, through minimum distance. Is it clear? First, we find out from S to this ABC minimum distance. Next, S to this D, E, F at minimum distance possible, how to reach these nodes. And then finally, we have to find out to reach T, what should be the calculation. Okay, to reach from S to T, minimum of, okay, minimum of what? Minimum of S to D. That is, we have already reached from S to D. Okay, that minimum, that distance we know, that distance is 5. Okay, from here to here. And then from D to T distance. Okay, distance from D to T. And we have reached from S to E. And then from E to T. That is S to E plus E to T. And then S to F and from F to T. Okay, distance of S to F plus F to T. So we know the distance for these three things, minimum distance, that is 5, 7 plus 7. Okay, 5, 7 and 7. 5, 7 and then 7. Now we also know the distance from D to T, E to T and F to T, that is 18 plus 13 plus 2. Minimum among all these things is 7 plus 2. Okay, 7 plus 2. That is the minimum distance from S to T. Either forward approach or backward approach, you will get the same result. Okay, you should get the same result. In exam, they will ask this one question will be there. Okay. For multi-state graph, find out the shortest path using backward approach or forward approach. See, you have to draw a graph with the directed edges, with weighted edges. You have to draw a graph, and you have to solve it and show which is the minimum path. Okay, and in textbook 4 or 5 line same thing. It is represented in algorithm. Some pseudocode is present. Okay, I have not put it on the slide. Forward approach, one algorithm is there. Backward approach also. It's not algorithm. 2 or 3 steps he has explained there using I and J. That also you need to write. See, you have to write those two. That is the algorithm present in the textbook. Okay, some pseudocode it is present in the textbook. When this question is asked, you have to write the graph on your own. You have to solve it and tell which is the minimum path from S to T that you need to do, and you also need to write down that pseudocode, okay, which is there in the textbook. See, these things will be asked for 8 marks or 10 marks. To get full marks, you have to write everything. Is it clear? Those things you need to write. There will be a question, sure short question on this one. They will not give one new graph and ask you to find out. They will ask you only because drawing this is not an easy thing in question paper. For that reason, they will simply ask the direct kind of theory question. You have to draw the graph, and no need to by heart these things. Okay, just draw a simple graph and solve it. Either backward or forward, they will ask. Solve it and write down that pseudocode. Okay. And once if you see the graph itself, easily you can find out what is the solution. So you will not make any mistakes. You should not make any mistakes when you are solving this problem. Okay. Next, advantages of dynamic approach. See, may a few more algorithms are there in dynamic. This is one example. Okay, we can avoid searching the entire solution space. Uh, because you need not have to, like as I said in the Fibonacci, you need not have to call all Fibonacci. By substage results will be there which we can use, and we can solve the problem stage by stage systematically, and store the intermediate solution in a table so they can be retrieved from the table in larger stages of computation. Okay, as we saw in Fibonacci, or here also distance calculation. For nearest node, we'll calculate the distance and we'll keep storing it in array. So when you're calculating for the last node, simply we can make use of the distance calculated earlier, and we can finish the computation. Okay, so that is about multi-stage graph forward and backward approach using dynamic programming. Tomorrow we shall see about knapsack using dynamic approach. Okay, all of you, I will stop here today. Mark your attendance. I will continue in the next class.